You've come to the right place, mathletes. We're in 5.1 again, and this time we're going to talk about area under the curve. And so we're going to kind of connect that with our sigma notation and summation. And so here we have this is a situation where, or this is kind of what we're after, is we're trying to find what is a way to find the area underneath the curve from a bounded region. So we're bounded from A to B. So we want to find the area basically bounded by those endpoints on the left and the right, the curve on the top, of course, and then in the x-axis on the bottom. Okay, so we want to find that. We want to be able to find that area there. Okay, and we don't really have a great formula for it, right, in geometry, because it's not a uniform shape or a shape that that we know, right? We're just trying to find the area of some under some curve, right? And so it's going to be, and this could be different depending on the curve. So this gives us a lot of versatility if we can do it. So there's one way to approach this, and is to create shapes that we do know within this, right? And sometimes you'll see trapezoids, and that's actually one of the more accurate ways to do it. But kind of the common way is to use rectangles to figure out, okay, maybe we can break this up into rectangles, right? So like we can get a rectangle here, and maybe a rectangle here, and a rectangle here, right? And this isn't, just take this one. This isn't exactly right? We're missing some, like these rectangles are a little too much here and here, so we have a little excess, and then they're a little short here, so we have a little we have a little shortage here. So with these rectangles or whatever shapes we choose that aren't exactly, don't align exactly with the curve, are going to give us either excess or some kind of shortage, right? But they give us an approximation, and so we're going to start there. So there's two ways to go with our rectangular approximations. One is left endpoint, where you start on the left, and then you have these uniform intervals, and the width of each of these we call delta x. Okay, so each of these widths is delta x. Okay, and then the height of each of these rectangles is f of whatever these x values are, right? So here, like this one would be f of x sub 1, right? And this would be f of x sub 2, okay? And then f of x sub 3 and so forth, right? And we could go all the way to x sub n, okay? All right, and so a is the first and b is the last, right? X value, all right? Okay, so with the left endpoint, we start at A, and we go and we keep making these rectangles at these regular intervals, which remember we call delta x. And then we could find the area of these rectangles, right? We know area is length times width, or base times height. And so in this case, it would be the height, which is f, right? F of whatever it is, right? F, in this case, f of 0 for this rectangle, right? Times the width, which is delta x, right? Delta x is the width of each of these, so they're uniform. So then you would just sum these up, right? You would just sum up each of those rectangles. So that, like, this could be where the eye goes, right? And then we could create a sigma notation and say, hey, what if we start at 0 and go all the way to n? Let's find the sum of these, right? And actually we go to n minus 1 for left endpoints, right? Because we don't actually use this this value, we use this one right before it. Okay, so that is how we get this right here. And so it's a little different than what I said. Instead of starting at 0, we still start at 1, and then we just make this I minus 1. And so if we plug in 1, we get x sub 0, right? And then that way we go to n, and when we get to n, that's going to be n minus 1, right? So that'll be the highest we go. So notice that this is the height, right? Or the let's call it the length of our rectangle, and then this is the width of our rectangle. Okay. So all this is just saying, hey, let's sum up all the rectangles from 1 to n, and that'll give us an approximation of the area under the curve. All right. So this is left endpoint approximation, and we'll see right endpoint next. But pretty much the difference is where you start and where you finish. Okay. So with left one, we start at x sub 0 and we end at n minus 1. Okay. And this is the sigma notation version, and this you can kind of see how it works out. We're just adding the first rectangle area plus the second rectangle area all the way up to the last rectangle area. All right, now for right endpoint. So this time we're not starting at x sub 0 for our height. We're starting at x sub 1, right? And then x sub 2, x sub 3, x sub 4. So we so anyway, this is f of x sub 1, and then we still have the same width delta x. It's going to be uniform, and so it's the same idea as far as finding the area. We multiply the height, which is the output at these given points, right? So we keep having all these outputs, and these are the heights, and then we multiply those by the width, right, which is our delta x, and that gives us the area. So that's how we get that's how we get our right endpoint. We start at 1 and we go all the way to n. Okay, so this one's a little looks a little cleaner because you don't have the I minus 1 in there, but same idea though, right? So this time we start at x sub 1 and we go all the way to x sub n, and we're just taking the area of these rectangles, length times width, right? And so here you can see this is the first rectangle, second rectangle, all the way up to the nth rectangle that we're adding the areas for. Okay, and just to go back to the figures, so you can see that, you know, they, like in this case, depending on which way the curve is going, like here under the curve we see with the this is the left endpoint, we see we have a shortage, right? But under the same curve with the right endpoint, we ended up with excess. And so but if we were on the other side of the curve, it would be the other way around, where the right endpoint would give us a shortage and the left endpoint would give us excess. So with the right and left endpoint, we kind of have some, they're both they both can either give us excess or shortage in any given situation. So you know, so it kind of depends on the curve as to which one, you know, maybe fits better. But yeah, and there's a couple others that this book doesn't talk about, where you could actually you could have a center point for your rectangle, and then, like I think I mentioned before, you could have trapezoids, right? You could also do circumscribed or inscribed, where you do a kind of a combination of left and right depending on the curve. You would either go from the inside or the outside. So those are things that we won't get into, but there's a few different ways to do this beyond left and right. And there are few ways to do this besides just rectangles alone as well. So trapezoids are a little more accurate, but yeah, we're just going to stick with rectangles to keep it simple, and that'll give us everything we need to set up the definite integral, which is what we're leading towards.